We begin. What are we struggling with? Are we recording? Yes. I mean, in chemistry. I suppose we could talk about other things, but if it's out of my area, I might defer. But dating, relationships, I could handle that. We can do that. RS. What else?
The last structures that we drew, I don't understand how they are
Oh, okay.
beside their own.
Okay, we're going to do that again. Fisher projections. Okay. What else? So we're going to have a quiz on Friday, review on Friday, and then the exam is after break Wednesday. Okay, that's the new schedule. All right, so let's do R&S first, okay? So let's say I have, let's say I have that, okay? So I have 2 bromo, 2 chloro, butane. Okay? First of all, you don't want to waste any time determining whether or not it's R or S if it's not a chiral center. Okay? So you want to just quickly look at that and say, is that a chiral center? Yeah, it's got 4 different things attached. A methyl, an ethyl, a bromine, and a chlorine. Okay? So then you want to, the next thing you want to do is you want to prioritize the groups, okay? So in the nomenclature system that we use, we prioritize the groups based on atomic number, okay? So it's atomic number. So if we look at this, which of those 4 groups on our stereo center has the highest atomic number? Bromine, right? So it's going to have the highest priority. Okay. The next priority is going to be chlorine. Okay. And then you kind of get to this where it gets a little bit fuzzier. So it's still the same. Here's where you can go wrong. Okay. It's still the same exact system that we're going to use. It's still based on atomic number, but what's going to confuse you is you're going to say, oh, it's based on size. Okay? So you're going to say an ethyl group is larger than a methyl, so the ethyl is, the higher priority. Well, that's true in this case, that the ethyl is the higher priority, but that's not the reason. Okay? It may work most of the time, but I might find something to throw out there that kind of sinks that wrong way of thinking about it. Okay? So the way in which you do it is you go out to the next. So I'm going to draw out these hydrogens here. Okay? I'm going to draw out those hydrogens. So you go out 1 atom and come to here, and you go out to 1 atom, and both are carbons. So both are ties. So that they both have a atomic number of 6, so they both tie each other. So then you go out 1 more atom, and in this case I go out to a hydrogen, and in this case I go out to a carbon. Okay? Right. I know I'm going to. Fine. I can keep doing that. So we can do that. We can go here hydrogen tie. Here hydrogen tie. Here hydrogen, here methyl win. Sure. Every time it should work just the same. But might as well pick the group that because I wrote the last exam way too short apparently because people finished way too early. So we're going to I'll have to double the size of that exam, so no, I won't do that. But you want to conserve time. Your time's important. You want to work diligently. So just go to the one that you know is. And if you have another example here, we can do it. Okay. So then that makes this whole ethyl group here 3, and it makes this 4. Okay. So the methyl 4. So most of the time we have the hydrogen being the loser, right? And we say, oh, and you put the hydrogen towards the back. Well, in this case, I have a methyl group that is the 4th priority. Okay? So I'm going to put the methyl group towards the back. Did I lose? Who did I lose? Okay. So most of the examples that we had, let's get another example. Let's get another example. Let's do it this way. Okay, so let's use this example. Let's just pause on that one for a second. I won't pause the video. Okay, that's supposed to be a dash. I didn't quite get it. Okay, so here let's just go through the same process. Bromine here is going to be the highest, right? We all good with that? And the next one is going to be this ethyl, and the next one is going to be this one. So here, hydrogen is the 4th one. Okay, so we're normally, you know, it's nice and easy. You set up the problem to where hydrogen is your lowest group, it's atomic number of 1, and it's going back. So this is a win-win for us. We can quickly determine this one. Yeah? Right, just the same winning reason here. So I come to here, then I go out 1, I come to here and I go out 1, and it's a carbon instead of a hydrogen. Exact same reason. Okay? Okay?
Could you redraw that molecule with the methyl on the back?
I can.
Will you? Could you?
Okay, when we get there. We're going to do it 2 or 3 different ways. Okay? Because, you know, if I just did it one way, I think isn't there like a question on the evaluation at the end that the professor had multiple ways of explaining problems or solutions? I think there's some question on there like that.
You're saying we can't say that.
So now you can't say that, right? Okay. Or I could bring donuts on that day, refreshments. Usually you get higher evaluations if you bring donuts. So, any of your professors bring donuts on? No, they're online now. You don't. At Boise State, they did.
Oh yeah, because she knew she wasn't going to get a good one.
That's great. That's great. I've been dean quite a while, and so I get to see all the faculty evaluations. And a person that is gone now, maybe you know him, Leon Powers. Always got the highest evaluations of anybody. Always has got the highest evaluations. Nicest guy, biology professor. Talked about fuzzy things all the time. So it was all, very nice and good subject matter to teach. And then on your birthday, he had your birthday written down, and you would come into class that day, and he'd have a box of animal crackers on your desk to celebrate your birthday. And he always brought donuts on evaluation day and all this kind of stuff. And he just had all the tricks. And he was a great professor. All right. So are we in agreement that bromine is the highest priority? Who's not in agreement? It's okay to raise your hand. Who's not in agreement of this priority system? Bromine, then the ethyl, then the methyl, then the hydrogen. Are we all good? We in agreement with that? Because if I've lost you here, you're really lost. So, okay. So then, what you want to do is you want to put your eye and direct your eye to put that hydrogen going to the back. So really, what you want to do is kind of put your eye, that hydrogen is going right to the back of the room. You want to put your eye right about here, okay? So that hydrogen is kind of going up and back. And so if you do that, and I look at that carbon, I've got my ethyl group going that way, I've got my methyl group going this way, and I've got my bromine coming up here. Okay? And so if I go 1, 2, 3, my progression is this way, which is R. Okay? So you just try to put your eye there. Okay? All right? Did I get it right? Okay. Clockwise. R is clockwise. Okay? All right. But here, we have the methyl as the fourth group. Okay? So I didn't set it up quite as easy on this one as I did that one. But it's the same sort of thing. Now, if you can imagine what you want to do, just put this in your head, and I'm going to do it. I'm going to redraw it as well. But put your head right over here. Okay. Oop, that's not a very good eye. That's an eye that needs an ophthalmologist. Okay. Put your eye right over there, and just imagine yourself looking down, and you're looking down this way, and that methyl group is going straight back, and you've got the chlorine out here, you got the bromine over here, and my body is kind of the ethyl group, and you go 1, 2, 3, still R. Okay? Sorry, I messed up. I had my bromine on the wrong side. My bromine is over here, it's going back. My chlorine's over here. My body's over here, so it's 1, 2, 3. So that's S. Okay, so that's one way of doing it, just getting your head in there. Okay? The other thing you can do is you can just flip it. So this gets a little bit harder, but you can redraw it. So if I take the molecule and rotate it, let's see here. So I'm going to rotate it kind of this way some, okay, and try to get that methyl group in the back. So I have my carbon. So when I do that, let's see here. Okay, it's going to take me a second here. So if I rotate that back, my chlorine comes here, and my ethyl stays the same, and my bromine is up here. Let's see if that worked out. Yeah, that worked out. Okay. How did I do that? I've looked at them a lot, and you kind of get your head in there, okay? The other thing you can do is spend a good amount of time with your kit, or the kit that's in the kits are still in there in the organic lab. So, for example, let me make this one real quick, maybe. Okay, so what do you like better? Chlorine is usually green. Oh, look at that. Had a 50-50 chance. Chlorine is usually represented as green, okay? And bromine is usually purple. And so here I've got my chlorine coming forward, my bromine going back, my ethyl group on this side, my methyl group on that side, okay? So then I'm just going to rotate this like that. Yeah, that's what happens. Remember, What we're really doing here is preparing you to do really good arthroscopic surgery on me. So at some point in the future, I'll probably need my gallbladder out. I don't want that big scar, you know. I want that little scar that goes in through my belly button. That's what they do. They got the scopes and everything. I already had arthroscopic knee surgery. That was great. That was, anyone had arthroscopic surgery? Boy, you guys are just so healthy. Arthroscopic, I walked out of the hospital with arthroscopic knee surgery, okay? And up 3 flights of stairs because we didn't have an elevator. And then I was kind of crashed for a while, but yeah. All right, so got to get your head, I'm just giving you some time to get your head to think about that for a second. Can you get your, all right. All right. You want to do the same thing as if you draw the mirror image of this. So if you draw the mirror image, let's draw the mirror image of this. So I got a carbon, I got an ethyl, I got a chlorine. I got my CH3 going back here, and I got my bromine here. Is that the mirror image? Can you draw the mirror image things quickly? Oops, sorry. It's actually the same, but it was actually right, but because those are going straight forward and straight back, but it looks better that way. Okay. So do the mirror image there. There again, now the methyl group's going back. Identify our groups here. 1, 2, 3. 1, 2, 3. That's definitely R. And so if I have one stereocenter and it's S, then it's mirror image. The stereocenter has to be the opposite, which makes it R. Okay? And they must be enantiomers. If I have this in a bottle, I have that single stereoisomer in a bottle, it is the S stereoisomer. If I have this isomer in a bottle, I have that single stereoisomer. If I put this one in a special machine and do I can't think of the word. Help me. Help me again. Polarimetry. Somehow that word didn't want to pop out. Then this one is going to rotate light one direction or the other. It doesn't have to rotate light left. It doesn't have to rotate light right. But it will rotate light some direction. So let's say it is a plus 15. Okay? I just made it up. I don't know what it actually is. Then this one will be a minus 15. Okay? Okay, here's new knowledge. If I have a mixture of those two, I have a mixture of the R and an S, a 50-50 mixture of those. If I have a 50-50 mixture of those, my rotation is going to be 0 because the one's going to cancel out the other one. And we're going to call that a racemic mixture. Okay? Now, from lab, we've been isolating molecules from mixtures, right? So you did an extraction, you did a distillation, TLC, all those different types of things to isolate something from a mixture. Can you isolate the R and the S If you have a 50-50 mixture of R and S, can you isolate one from the other? If you smelt this one might smell like juicy fruit gum. This one might smell like farts or something. Okay? They could smell very different. All right? But, right, we did that. But if you have a 50-50 mixture, could you separate them? The answer is yes. It's called a resolution. Okay? Resolution. Okay? You can do a resolution in a lot of different ways. Basically, this is you're going to have to pay attention real closely here. Okay, so these words are gonna, I can't write down all these words, so you're gonna have to pay attention to these. If you have a chiral substance by itself, a single, like if you had just the S, okay, it acts as if it's a chiral molecule. Okay, it'll rotate light. You can tell the difference between it. If you have the other one, it's the other one. If you have a mixture, it acts as if it's not a chiral substance. So if you take the color of those two would be identical. Okay, so every physical property would be identical. The boiling point would be identical, or the melting point would be identical. If you did an infrared spectrometry experiment on them, it would be identical. If you did a nuclear magnetic resonance spectrometry experiment on it, it would be identical. Everything is identical unless you put it into a chiral environment. Okay? So when you smelt, so if we take, and so if we take, this one is, let's say this one is S, actually is R. Let's say this one's S, this one's R, and I mix these back together 50-50, and you smelt it, you would all smell the same thing. It'd smell weird, but you'd all smell the same thing. But its spectroscopy would be identical, okay? You wouldn't know that I had a mixture. If I take them and I separate them, you wouldn't know that you had chiral compounds unless you put them into a chiral environment. Like your nose was a chiral environment, because your nose is made up of proteins that are all chiral. So you smelt this one, it smelt like pickles or something. You smelt this one, it smelt like evergreen, okay? Because you put those into a chiral environment. So if you put a racemic mixture into a chiral environment, they will behave differently. So for example, if I make a thing and I put yeast in there, and I let yeast is a chiral, yeast is made up of a bunch of proteins, and the yeast might say, I really like to eat the R, but I can't eat S. So you let yeast chew on it for a while, and then all of a sudden you have it's reacted with all the R, and you just separate out all of your S. Okay? Because that's a chiral environment. Or you add to this, and this is going to be, let's just say that I can do an experiment here. So I add to this another thing that's chiral. Okay? So I'm going to add some molecule, I'm going to do some chemical reaction, and we're going to talk a lot about chemical reactions. You got a whole semester of chemical reactions. So let's say I add a chemical reaction to this, and so then I get, I'm not going to draw the molecules out, but I get S, which is plus, and then I've added on this other plus thing. and I get R that is minus, and I've added on this other plus thing. Okay? So this thing right here is something that's chiral. Let's make something up. Let's make up. I added that on it. Okay, that's a chiral substance. Let's say that that's, what is that? Is that R or S? 1, 2, 3. That's R. So this is R, whatever it is. So I take the S from that one and I add on this R thing. Take the S from that one and I add on the R thing. So now I have S, R, R, R. What's the relationship between these two new molecules? What's the relationship of these two? Enantiomers, right? What's the relationship between these two? Diastereomers. Okay? These are diastereomers. So now I've made 2 diastereomers. Diastereomer 1, diastereomer 2. Okay? The properties of diastereomers are that they are not the same. They can have different boiling points. They will have different boiling points, different melting points. One could be green and one could be blue. One could smell like rotten fish and the other one could smell like roses. Okay? They're different physically. Every physical property is different. They have a different infrared spectrometry, different nuclear magnetic resonance spectrometry. Okay? They could rotate light the same direction. This could rotate light. This one, if I ran this, it could rotate light plus 12, let's say, and this one could rotate light plus 120. Because they're very, very different. Okay? And you can separate them because they're different. So you can do a crystallization. You can just crystallize, and one will crystallize and one will stay in solution. One might be a liquid, one might be a solid. You can do a distillation. They would separate out on 2 spots on thin layer chromatography. Okay, so you could get 2 spots on thin layer chromatography, and then you could, I know this seems strange, but people do this, then you could just cut out each spot and you would have them separated. Okay? Now, you did these little tiny plates, but you can do plates that are like 4 or 5 millimeters thick that you can put a lot of sample on and then you can take them out. Okay? So you can separate those two. So you separate that into D1 and you separate that out into D2. And then you do another reaction because you set it up this way. And you get back out your S plus, your R minus, plus, put it up here, plus your R thing that you put on. Okay? And then you have this in a bottle, and you have that in a bottle, and then you've recovered that. You have 3 bottles. Okay? It's called a resolution. What's the main reason why I'm telling you this? Yes. That is one main reason. What's another main reason why I've told you this? Yeah, it's going to be probably going to be on the test. I really, really want you to catch this idea that 2 enantiomers have the exact same physical properties of each other, and 2 diastereomers have very different, or can have very different physical properties of each other. Okay, that's really the main thing. So different that you can separate them physically. you could crystallize them and look, and one crystal might be a cube, and the other crystal might be a needle, and you can just take a pair of tweezers, and just separate the two out. Okay? And here's the kicker. You won't argue with an organic chemist when you're a biochemist and you've got it wrong. Okay? Because I can remember back having to do this exact same lecture at a group meeting at the Veterans Administration. We were working on a molecule. Here, we'll put that molecule up. We were working on a molecule. Let's see here. Kind of similar. And then I'm going to do Fisher projections. Okay, so you got all that, right? So, if you don't write this down, it's okay. Doesn't look so good. I'm just going to write sugar here. And the sugar thing is a chiral sugar. Okay, that is doxorubicin. Okay, doxorubicin is a chemotherapy drug. It's the most widely given chemotherapy drug out there. Okay, if you're go to Tree City Church of the Nazarene, the pastor's wife has breast cancer, and she's taken doxorubicin. I'm following that on her Facebook posts. Okay, this is her treatment. This and about 2 or 3 other cocktails of drugs, but this mainly it. It's cardiotoxic is the problem. Is so you can only take a certain amount of it, and then you have to stop taking it, and hopefully that's put your cancer in remission, because you just can't take any more in your lifetime. Okay, but in the body, your body, which is chiral, does an oxidation. Now I know this is going to go somewhere. Okay, so it's a lot of drawing here, but not all organic chemicals are simple. Okay? All right. So in your body, there's this oxidation that takes place. And this OH is oxidized stereospecifically. This carbonyl is oxidized stereospecifically to that OH. Okay? So that's what they call the natural metabolite. This is really what causes cardiotoxicity. Okay? So if you do the same reaction in a test tube, okay? That's a reduction, sorry. And you do this in a test tube. So this is in a cell, let's say, in your body. Let's say you do it in a test tube, and you do the same reduction. You get the same molecule. Okay, I'm going to give you some. You're going to get some special. Bottom there. Okay, so you're going to get something special here. Okay, this is new knowledge for you. A squiggly line. What's a squiggly line mean? Huh? Squiggly line means both going forward and going back. Okay? So I didn't want to draw them both, so I drew the squiggly line. But there's this one, okay? And there's the one where the OH is going back. Okay? So you do this in a test tube, and you get both of these. So what's the relationship? So here I'm going to draw, so you got this one, got all that stuff out there, okay? And then you have this. So what's the relationship between these two? Because you get both of them when you do it in a test tube. What's the relationship between having that OH come forward and that OH go back? Okay, you say enantiomers. They're not. They're not enantiomers. Because this sugar thing is full of stereochemistry. May have tripped you up there a little bit. And that's stereochemistry right there. So I only changed one stereocenter. I did not change every stereocenter. So if you change every stereocenter, then that would be an enantiomer. But I only changed one out of about 8 stereocenters, so they're diastereomers. Comes back to this. I have not every stereocenter is exactly opposite. So they're diastereomers. Okay? So if you remember that, and you do biomedical research, you'll know that there's a difference between enantiomers and diastereomers. Okay? So, if you take this molecule and you remove that group, make that a CH2, and then this thing over here, you do that to it, you get a new drug. It's called GEM 150X. You can Google GEM 150X, and it's in phase 3 clinical trials for a new chemotherapy drug. Okay? And it's not cardiotoxic. So in the future, and it's kind of somewhat ironic here that I should have drawn this one in red, because and the other one, because doxorubicin is a highly colored red compound, and GEM 150 is a blue compound. Okay. Slight sidetrack, but it's going to lead right into Fisher projections. How many people did I lose completely? Some people are sleeping already, so I know that I've got to up my game. Infuse. You should walk around with an infusion of. It should be like in football. Football, you're like going, or not so much. I don't know if they do this in other sports, but you start getting bad cramps, and they take you in the back room for a second, and you come back and you're all good, right? What'd they do? They went back, gave you an IV of electrolytes. I don't think they do that so much in other sports, but so you get a little sleepy in class, send you over, everybody pauses, send you out on a little break, you get some caffeine, come back. All right. Okay, so let's say that I have that molecule. Okay? Is that molecule chiral? There is a hydrogen on there, right? I drew the hydrogen. The hydrogen is going back. Is that molecule chiral? It is. It's got 4 different groups. Okay? Is it R or is it S? Ooh. All right, so let's do our little thing. If I look at this carbon, come out to here, I have an oxygen. I come out to here, I have a carbon. Here I have a carbon. Hydrogen going back. So the oxygen definitely wins, right? So it's a 1. Come out to here, I have a carbon. Come out to here, I have a carbon. So there's a tie. Come out to here, I have a carbon and an oxygen. Come out to here, I have a carbon and a hydrogen. So this is number 2. It's going to be number 3, and then 4 is going back. So then that is R. Okay? So I want you to put your eye right over here and look right down that backbone. Okay? And then I want you to rotate it to where the CH hydrogen is up. Okay? So put your eye right there and rotate it so that this group kind of pops up there, the methyl group goes down, and I want to have both of these groups up. And this is going to be back. Okay? So the CH, so the aldehyde is, yeah, so I want you to say which one goes which direction. If I put my eye there and kind of, which way? If you look at that down, does the OH go, okay, well, this door number 1 or door number 2? So this would be door number 1. This is door number 2. So which way does it go? Should I get my clicker out? You're confident it is 1.
Oh, you just have to do it opposite way.
Okay, we'll do an unofficial survey. Unofficial survey. Everyone has to vote. Okay, so I don't have my clicker out. It takes a little time to get the technology going. You ready to vote? Everyone has to vote. If you don't vote, you lose 10 points on the quiz. All right. I have my. Remember, I still have my implant in my eye. I record everything. All right. You don't believe me? You're like, okay, ready? Number 1. Raise your hand if you think it's number 1.
What do we touch?
Number 1 is the OH goes here. Number 1, the OH goes here. Raise them high. Okay. So we got 1, 2, 3, 4, 5, 6, 7. Number 2. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. About, I don't know, about, we'll say about 24. Okay, so it's democracy. So it's got to be number 2, right? Who, okay, be honest. Who didn't raise their hand? Or who looked around to see whose hand was being raised and raised their hand to be along with that person? All this psychology. Okay, goes here. All right, you're very confident, I know. So if you put your eye there, so let's see if I can get this. See if I can get this. Where'd my molecule go back there? So here again, you need to. So what do I have? A methyl, a hydrogen, and an OH. Should have left that on there. I don't know. Let's see if I get the right one. Okay. What did I do here? I think I was right. I just didn't twist it right. Okay. So here it is. I've got my hydrogen going back. My OH, this is my OH here. OH coming forward. Methyl group going down, and then this aldehyde coming over here. Okay? Aldehyde over here. So I'm going to put my eye right here, and I'm going to look down that right there, and I'm going to kind of rotate this way, and then I'm going to draw that on the board. And the OH ends up on that side. These two groups are coming straight towards you. Those are going back. Okay? Yes?
So why did you decide to put the carbon positive?
Okay? The formal
The methyl group on the top of bottom?
wouldn't matter.
Wouldn't matter. Okay. It's just how you want to orient the molecule.
Yes and no. Okay, so let me get back to you. So when you do a Fisher projection, you just take that, and that's what that means. That means that these groups on the side are coming towards you, and these groups in the back are going away. Okay? Why did I put the CHO up? That's the way everybody draws a sugar. So I just did it that way. It could be down. Okay? Another sugar, we could do this one. I don't know what sugar this is, but this is a typical way in which you would draw a sugar. Okay? How many stereocenters? Ooh, this is a good question. How many stereocenters in this sugar? Three. 1, 2, 3. Okay? Not a stereocenter here because it's a CH2. So then if I have another sugar that's pretty similar, what's the relationship between those two sugars? Those are enantiomers. Because they are the mirror image of each other, and you cannot superimpose them. And the only way in which you can move a Fisher structure is you can only move it in the same plane as the board. So you can't flip it over. Because if you flip this over, everything that's going back is coming forward, and everything that's coming forward is going back. So you can only move them in the same plane as the board. So I could just try to put this over the top. Or I could rotate it 180 degrees, but I can't flip it over. Okay? How about this one? What's the relationship between this one and this one? Yes, this is a diastereomer to both of these, because we can determine whether or not that's R or S, and that's R and S or R and S, R or S. I'm going to make this up, so this is not going to be true because I don't have time to go through it. But let's say this is R, R, S. This has to be S, S, R. Okay, I just made that up. I'm probably wrong. I'm probably wrong half the time because I just made that up. Okay, this has to be S. Based on this, has to be R, and this has to be S. Or I'm sorry, R. Because this is the same stereochemistry. That's the opposite stereochemistry. That's the same stereochemistry. So if I have RRS, the enantiomer is going to be SSR. Anything else is going to be a diastereomer of those two. So if it's SRR, RRR, anything else is going to be a diastereomer of those two. Yes?
Can you tell if it's R or S just from the picture projection you have to actually draw out?
I can. I put my head right over here because I know this is coming forward, so I get my head situated here. The OH is going to be 1. The CHO is going to be number 2. So, unfortunately, I guessed wrong. It's S. Okay? Oh, no, I guessed right. Because I put the hydrogen right towards me. So, yeah, it is S. I'm sorry. I got to flip it. It's R. It's R. I guessed right. Did I guess right here? I think I guessed right. Yes.
So enantiomers are the same two molecules, and diastereomers are like a third molecule.
No. If I have this molecule, if I have those don't pretend that's not there. What's the relationship between those two molecules? Diastereomers. Enantiomers are what? Yes, non-superimposable mirror images. Diastereomers are what? No, that's the same molecule. Not mirror stereoisomers that are not mirror images. Stereoisomers that are not mirror images. Okay, a 7 iron and a 9 iron. Okay, we will see you on Friday. Thank you for a good class. I think